thought that we could look at an example of MapReduce package, and then maybe a couple of exercises. However, if you have any other suggestion, since we are few, so maybe we can manage to discuss something else if you need that. Otherwise, I can go on and show you something with MapReduce. Okay. Okay, first of all, I could not find a Hadoop installation on these computers, at least nothing that I could find. So I put all the necessary installation in my home directory. It's this one. I think that you could set all necessary pointers to my directory. So I prepared a short script that you can get with this command. Okay, so wget and so on. Okay. In there are just a few environment variables that you need to run computers on, to run Hadoop in these machines. So after downloading that script, you should have hadoop.sh on your home directory. Then you can run it using the source command. And after running it, you should see, for example, the environment variable Hadoop home. It should be set to this value. If you can confirm that you can do it, then we can proceed.
Does it work?
You did not run the source. So now you should have the Hadoop command. If you type Hadoop, you should get a help message with all the possible subcommands of that program. So Hadoop is just a utility that manages all aspects of a MapReduce system. It manages the distributed file system and of course the scheduler and so on. So, just to see how it works, I propose to look at the hadoop.apache.org, which is the home page of, sorry, I took 3 O's. And in particular, you can find a tutorial going to Hadoop command. Getting started. No, so okay. Learn about Hadoop. And here you find the MapReduce tutorial. So here it explains a few, with a few words of what I said yesterday in the lesson. So you should recognize here the different key value pairs that are transformed by the 3 functions map, combine, and reduce. What I suggest here is that we follow this source code and try to run it. Maybe understanding what we do, of course. So, start by editing okay, what's the name of the class? Okay, word count. So let's edit the file word count.java. Next, I don't know if we should rewrite. Okay, let's just copy and paste the text of the program. Of course, this gives us a few line number to get rid of. Anyway, let's look at the source code as long as I correct it. Of course, we are importing a lot of packages. Actually, all these packages are located within the Hadoop 101 directory, and in particular they are in this Hadoop core jar file. Okay, so everything we need for our Java tutorial is the core library of the Hadoop package, which is here. And in fact, if you look at the class path environment variable, you see that it points to this file. So that if you run Java or JavaScript to compile, it will look into the package. Now, let me remove a few line numbers. So, the first thing that you find inside your class word count is this public static class, this inner class, that defines your mapper. So your mapper is defined as an extension of this MapReduce base class and implements the mapper interface. The mapper interface depends on 4 types. It's a generic interface with 4 types, and you should guess that these 4 types are in the order: the input key, the input value, the output key, and the output value. In fact, this class that is going to count the number of words in a set of documents receives as an input, okay, a key that is the document identifier, which we don't care about in this example, but again, we get it. Text, which in this case will be a line of the document, and it outputs a key value pair where the key is text, because we are putting out the single terms together with a value that is integer. Here you see that it actually redefines some integer values, the long value and the integer value, as long writable and int writable, which is simply a wrapper of the common long and integer types that are used in order to be able to put them in the streams that it's using internally. So we need some specialization of integers and longs in order to use them with the MapReduce framework. Now you see that this class only defines one single method, the map method, which is contained in this interface mapper. So of course you have to implement it. The map method requires a key value pair in input. Okay, the key will be something related to the document, as I said. The value will be, we can assume that it's going to be a line of text, and maybe it can also be the whole document. Anyway, it's text. Then the third parameter is this output, which is of type output collector. It's the data structure that receives the output tuples generated by the mapper. And finally, a reporter object that we are not going to use, which is used for reporting, of course. So in order to allow for some exchange between the mapper object and the MapReduce manager that dispatches jobs to processes. Okay, so what's important to us is that we receive a key, a value, and then we are told where to put our output tuples. Next, okay, value is of type text, which is a specialized type internal to MapReduce, but we have the toString method that converts it into a common Java string. Then we can use the standard Java tokenizer to tokenize this line of text, and then as long as the tokenizer finds more tokens in our text, in our case, of course, we assume that we have words separated by spaces, so tokens are single words. Okay, what do we do for every word? Well, you see that here two objects were defined in the class. The first is the constant 1, because you know that the mapper must output tuples in the form word 1. So here the code just prepares for a constant 1 that is going to be output repeatedly, and then we have this object word of class text, which is initialized as an empty text, but that every time is set to the value, to the new token. So for all tokens within our line, we set the object word to that token, and then we use this method, output.collect, that puts this key value pair, the key is word and the value is 1, into the output object. Okay, so map is going to put into output many tuples in the form word 1, 1 for every word contained in the input value. Now, the counterpart of map is reduce. Let's see how it works. Again, Our reducer is another class. Again, the class will extend some internal class that provides for some utility methods that are used by the framework, MapReduce based. It implements the reducer interface with, okay, in this case, 4 types that are input and output types. And in particular, you see, okay, the input key is text, of course. The input value, actually, you see, the reducer will receive a list of input values. But here we declare the value of the single input element. So we know that the object that reduce is asked to work on have key, text, and value interruptible, integer. And then the reducer is going to output a key. Okay, in this implementation, actually, the reducer explicitly outputs a key and a value. So the reducer actually receives a key in the form of a text token, then a list of integers in the form of this iterator, which iterates on interruptible objects. Again, we also receive an output collector object that receives the output tuples, which are in the form of text and integer, the second 2 types, and then the reporter objects that we are not going to use. And in this case, we just declare variable sum equal to 0, and then for every integer in the values iterator, that has next, of course, iterates on values. No, actually the get iterates on values. Okay. We add all elements in the values iterator into sum. So we are actually adding lots of ones together. And finally, we output the same key value that we got in as an input, so the same term, and the value sum, which is an integer, but of course to put it into the output collector we need to convert it to generate this interruptible, to wrap it into the interruptible object. Okay, so this is all we need to generate the MapReduce framework. Okay. Now, of course, we need a few definitions to make everything work. So here is the main. Okay, so the main just, well, now we interact with the MapReduce framework by this jobconf object. Okay, for job configuration. This job configuration object requires, at construction time, the class of a class that wraps the two inner classes map and reduce. Okay, here so we are just providing our jobconf object with the necessary information of where to find the mapper and reducer classes. You see that the two classes are declared static, so we actually pass them as class. Okay, next we just set a name for the job, but this is only for logging purposes. Next, we define all the types that are used in our MapReduce implementation. So, for example, here we say that the final output has a key of type text and a value of type writable, which is our actual final output. Now we tell the jobconf object that what are our mapper, combiner, and reducer classes within our overall class. Okay, in this case, map is used as mapper, reduce is used both as a combiner and a reducer. Next, of course, we need the framework to be able to work with different kinds of data. They could be binary data, they could be some XML encoded data. In our case, it's text, it's pure text. So we set the input and output format of our job to text input format and text output format that are two predefined classes that manage text input and text output. So that we work on human readable files and we generate human readable files. Of course, you are free to define your own format classes depending on the format of the files that you're going to use. I mean, there are, of course, interfaces that allow you to create different formats for your data. Finally, we define where to find the files that we want to use, where we want to work on. And you see the files are provided in the first argument, in the argument list of the main function. So when we actually call the system, we should provide an input path and an output path. The place where the system can find all the text files it should work on, and the system where the path where the system is going to put its results. After defining this, we just need to invoke the static method runJob of our job client class, which is defined, of course, in the framework, passing the configuration file. Okay, so in order to have this work, well, let's see if it compiles. So let me save it. Okay, to make it work, we need to create a jar file. But anyway, you have all instructions here. Actually, it's going to be a little simpler than this. So, let's create a directory, this word count classes, where all classes are going to be, all class files are going to be stored. Next, we need to compile our Java file. You see that here the syntax is rather complex because they set the class path on the command line, but actually we already have this class path defined in the shell file that I provided to you. So what we actually need is to compile using as a class directory word count classes the file wordcount.java. Okay, so after this you should find all the package hierarchy inside the directory word count classes. You see there is an org, my org, and then the classes. This is because I didn't bother to change the initial lines, so the package is inside the org.myorg hierarchy. Of course, you can change it if you prefer to have other paths. Anyway, everything is in the word count classes directory. Then we can easily create our jar file by using this command line. Okay, here we create, where is it? Okay, the Java archive, we create and view while you create the file. Oh, sorry, it's not usrjo, it's just wordcount.jar. Okay, so we want to create wordcount.jar using the contents in wordcount classes. Is the record. And here we are. Now we have added all the class files in our jar, and you can find wordcount.jar in your directory. Okay, next we have to work to create some input files. The input files should actually be placed in a distributed file system, in a DFS system. But since we are working on a single machine, we can simply create an input directory, let's call it input, and then place a couple of very simple files in the input directory. For example, we can even simply write with echo the usual Bob loves Alice, and we put it in input slash file1 file, while in file2 we write Alice hates Bob. So that we have collected a few input files in our input directory. If you list the input directory, you find the two files that we have created. Okay, this is the easy way of doing it. Of course, this is, for example, here I could use echo ls because these files are locally stored in this directory. Actually, if they were in a distributed file system, I should have to use the Hadoop command. For example, in order to list, I must write Hadoop dfs -ls input. should have used something different from Hadoop. Oh, okay, next I will check what I should have used. Anyway, you see, Hadoop provides, the Hadoop command provides all the necessary utilities to not only run MapReduce jobs, but also to look at the distributed file system. Or I can use the Hadoop DFS-cat input file 1 in order to see the contents of file 1. Of course, in this case, it was easier to use just cat input file 1 because it's stored locally. Okay, now we have everything we need to work. We have the word count.jar file containing our Hadoop, our MapReduce implementation of the word count program, and we have the input distributed file system, actually local, that contains the files. Now we just need to run Hadoop jar word count.jar. Okay, here now we want to invoke to start the word count job. So jar is the subcommand that looks into a Java archive. The first argument, of course, is the name of the Java archive. The second argument will be the name of the class containing the main function. We want it, and next we have the two arguments that will be passed to the main function. The first is the name of the input directory, the second is the name of the output directory. Okay, so jar, wordCount.jar, org.myorg.wordCount, input and output. Remember that here word count has a capital W and a capital C because it's the name of the class. And now, if everything goes well, we can start it and see, hopefully, a lot of output. Okay, you see it's a rather complex job just to count 3 words into files. Anyway, by following this log, you should see everything that the program has done. But first of all, let's go to see if the program has put something in the output directory. Okay, you see that the program has created an output directory, and the output directory contains 2 files. In particular, this part 000 contains our final result. Okay, so in the form token count, while probably success is just a flag file that tells that everything worked. Okay, in fact, it does not contain anything. It's just something that is put by the framework to indicate that the job is done. Now, if we try to rerun Hadoop, it wants to. We need to remove the output directory before rerunning the program. So the system assumes that the output directory does not exist. It wants to create it. Next, okay, we can have a look at the log, which is actually, well, it contains, of course, a lot of information. Okay, it recognized, for example, that there were two files to process. I'm looking if there is something interesting to see. But anyway, yes, there is nothing that deserves any comment, I think. Okay, so this is an example of MapReduce set to work. Now, what I would like to propose is some exercise that where you need to think a little about how to organize data in order to use the framework. Okay, so maybe I can use the blackboard. Okay, suppose that we have a set of documents. Of course, we assume that we have a large set of documents with a large number of tokens each. In particular, okay, but for the sake of the exercise, we have 3 files. Let me use the same terms that I used here. So, the first file is called random doc, and its content is, well, okay. I used rather random terms. Zigzag, bumblebee, slash, accord. I don't remember exactly why I used those words, but I prefer to use exactly the same term. The second file is called nonsense.txt, and it contains the words bumblebee, acorn, zigzag, slash. the third text, the third file, useless.pdf, contains the words acorn or dot bumblebee slash and zigzag. Now we want our system to output. Let me read exactly how I wrote that here. Okay, the aim of this exercise is to create an index that maps each term to the document where it occurs in the earliest position. So, for example, so we have a list of terms. Let me write the terms in alphabetical order. So we have acorn, then bumblebee, next dot, then slash, and finally zigzag. Okay, we have 5 terms. Every term should be mapped to the document where it occurs in the earliest position. So, for example, acorn appears in the 4th position in the first document. It does in the 2nd position in the 2nd document, and in the 1st position in useless.pdf. So acorn should be mapped to useless.pdf because it is the document where it appears before. For the same reason, bumblebee should be mapped on nonsense.txt. Dot actually only appears in the 3rd document, so it's mapped to useless.pdf. Slash appears in third position in random doc, while it appears in the 4th position in the other 2. And finally, zigzag, of course, is mapped to random doc. So, given these documents, we would like our MapReduce program to generate this mapping. So the question here is to outline a MapReduce-based solution to the problem. This means that you need to describe all input and output types, keys and values, and write down the mapper and the reducer. First question, input and output types of mapper and reducer. The second question is a combiner useful? A third, write some pseudocode of the mapper of the reducer function. Okay, I suggest that you try to think about it and maybe tell me if there are, okay, what problems you find in giving an answer to this kind of questions. Are the questions clear? Or, of course, if you have any problem in understanding them, of course, tell me that we need to discuss it, of course. Okay, can anybody propose the overall mechanism? So, what you expect the mapper and the reducer to do in order to solve this problem? So, remember that the mapper sees. We can assume that the mapper sees one document at a time. So one mapper just sees one document. What information should the mapper provide in order to keep all the information that we need for this problem? I mean, think of how you solve this problem by hand, in your mind. When you solve it in your mind, you need to look at a term, for example, acorn. You need to browse all documents in order to see the first occurrence of acorn in that document. For example, you need to see that, okay, here acorn appears as the fourth term, and you keep that in mind. Then you look at the second document, you find that acorn appears in the second position. At that point, you discard what you knew before because the second position is more important for you, and you keep acorn in the second position. Next, you browse the third document, you find acorn in the first position. This is more important than the second position that we are taking in mind. So finally, you say that acorn is in the first position in useless.pdf. Finally, the problem does not ask to record the position, but only the file name. So you discard your information, but you keep the file. So, but the problem is that the first part of your program, the mapper, only sees one document. So it cannot decide anything. It can only say, okay, zigzag appears in the first position of random dock, bumblebee appears in the second position of random dock, and so on. Of course, at the end, we need to generate key value pairs where the key is a term. So, we can assume that the mapper will generate terms as keys, because the terms are the key information in this problem. What is it going to generate as a value?
With the position.
Exactly. The value will be actually a pair itself. So the idea, okay, I think I can erase this central part. When you take the first document and you feed it to a mapper, the mapper is going to generate a list of key value pairs. These key value pairs will be first as a key, the term, second as a value, the document, and the position within the document. Of course, maybe it's not the only way to solve this problem with MapReduce, but it's the first thing that I can come up with. Then it will generate bumblebee and associated as a value to the same document, of course, a random doc in position 2. And so on. If you do this, where every mapper will output the association of each term with a document and a position within the document, okay, after all mappers have worked on all documents, so a long list of key value pairs have been generated. You know that the next step is the sorting phase. Well, actually what I call the sort and aggregate. From the sort and aggregate phase, new key value pairs will come up. And you should remember that the key value pairs that come up of the sort and aggregate phase are in the form key and list of values. The list of values that correspond to the same key in the mapper. So in this case, for example, one of the outputs of the sort and aggregate phase will be the term acorn associated to a list of values, and in particular random doc 4, because one of the mappers reported that the term acorn appears in the 4th position of random doc. In nonsense.txt position 2, and finally in useless.pdf position 1. So this is what the sort and aggregate phase generates. For every term, the list of values associated to that term by the different mappers. This is provided as an input to a reducer. What is the reducer going to output? The reducer should look at these values and only output the one corresponding to the smallest position, to the earliest position. So you should simply iterate this list and keep in mind only the file name corresponding to the smallest value of the position. So in this case, it should output corresponding to the acorn key the value useless.pdf. Okay, so this should be the overall functionality of the mapper and the reducer in this case. Let's try to be a little more specific about the input and output values that correspond to that, to these specifications. So the mapper, the map function, we can assume that it's going to receive as an input the name of the file and the contents of the file. Okay, so of course, as I said yesterday, the actual form of the inputs and outputs depends on the framework implementation. For example, in the Java implementation, in the Hadoop implementation that we have just seen, the mapper is going actually to receive as an input a file ID, which is useless in our context, and the contents of the document. So the contents of the document can be seen as a sequence of words. Okay, a list of words. But actually, let's make a more comfortable assumption for us. Let's assume that the mapper can also receive as an input the file name. So this is the file name, and this is a list of terms in the document. Okay, we can assume that it's already tokenized, so when we write the pseudocode, we don't need to bother with string tokenizers and things like that. Just assume that everything is. Okay, what does the mapper produce as an output? Okay, the single key value pair produced by the mapper is in the form of a term coupled with a value part, which is itself a file name and the position where this term occurs in the document. I know that this kind of notation can be quite confusing. So I'm not expecting that you follow this notation when solving the written exam. You can also write it in words or maybe yes, be a little more explicit in what you expect the input and output to be. Of course, here the mapper will output whole list of these, the whole sequence of these. So this is the prototype of the mapper. So it receives as an input a file name and the terms contained in the file name, and it outputs a list of terms, each term associated to the file name and the position of the term within the file. Next, the reduce function will receive as an input, as a node, a single key, which in our case is a term, one of the terms that are being output by mappers, associated to a list of file name and position. So a list of values as they were output by the mapper. And the final output of the reducer is the same term associated to a file name. Let's write explicitly the code, well, pseudocode of course, of the mapper and the reducer. So our mapper so again, what does it receive as an input? As an input, it receives a string, which is the file name. Actually, in the Hadoop implementation, we would not call it string. It would be a text type from which a string can be extracted. But just let's keep the things simple. I don't want to bother with the actual implementation. Just look at the basic things. So we can suppose that the mapper receives a string containing the file name and a list of strings which are the document contents, a list of terms. So, what the mapper does is just for every term t in the list terms, it's going to write out, to send out, emit, or if you want the Hadoop implementation, you would also have an output collector here with the method collect to write out. But anyway, what it's going to send out is a key value pair composed by the term T as a key and two pieces of information as a value. The file name and the position of the term within the file name, within that file. So we actually need to keep track of a position by initializing, for example, P to 0, and here writing P and increment. This is our method. So it's going to output zigzag in random.1, bumblebee in random.2. Actually, no, it starts from 0. Okay, so zigzag random.0, bumblebee random.1, slash random.2, and acorn in random.3. And so on. The other mappers will take care of the other documents. Next, the reducer. Will receive, again, a key and a list of values. The key, in our case, is a string. Let's call it T, term. The value, the list of value, is actually a list of, here we need to improvise some syntax, but so it's a list of pairs where a pair is given by a string and an integer. And this is the list of values that we receive. Okay, now the reducer needs to browse this list of values and keep in mind which was the pair having the lowest integer value. So for example, let's keep in mind the position P. And for all values in this list, well, we need to let's do it by counting. So we want to find a minimum, so let's start by assuming that the minimum is in position is the element of index 0 of this list. Then we increase an integer from 1 to the number of elements in the values list, and if the ith element of values, actually the second part of this pair is smaller than the corresponding in position P, we replace P with an in position I. So at the end of the iteration, P is the index of the value having the lowest value in the second member of the list. And finally, we need to emit corresponding to the term T values of P point first member in the pair. And this concludes our reducer. So among all string integer pairs, find the one with the lowest integer and emit the corresponding string. This associates every term T with the name of the file where it occurs in the earlier position. Actually, you see, more or less, what I have written here somehow supersede these kind of definitions. I mean, if you just write the pseudocode by specifying what the inputs and outputs are, that's fine for me. I don't need any more formal definition. So just focus on what the mapper and the reducer should take as input and provide as output. Okay, the second question, actually, well, this was the answer to the third question, actually, but the second question asked if a combiner could be useful in this case. What could the answer be? Yes. Yes, the answer is usually yes. Meaning that, okay, if we can process things locally, it's always better. Can the reducer be used directly as combiner? Yes or no? Not really directly, because this reducer discards very important information, which is the integer position. So actually, if we want to use the reducer as a combiner, we need to output both the first and the second element of the pair. Or we simply rewrite the reducer with that other information to have. So the problem of the combiner is that the input and output types must be the same. Otherwise, because it needs to join together the output of the mapper with the input of the reducer. Okay. So we can directly use a reducer as a combiner only if its output is the same that we would have from the mapper. So a combiner, let's write in green the changes that we need. Well, actually the only change is that instead of this, we output the pair, we simply output values of B. We stop here. Okay. So that the output is actually a pair, and not only the first component of the pair. Sorry?
Slash there is at the first position for this new documents. So in that case, we find.
Okay, so if there are some ties, some cases where I didn't consider the case. Actually, in the exercise, I wrote that that you can break ties as you wish. So in that case, for example, in this case, what happens is that I just put a less than here. So it means that the first document that you find is the one that you output. So this is fine for me. If there were also equal, of course, you would output the last. I didn't consider the case, in fact. Okay, of course, if any of you dares to write an actual Hadoop implementation of this problem, I would be interested in seeing how you deal with the different cases. I mean, you need, if you wanted really to write this in Hadoop, you should take care of some problems. For example, the fact that it's not really clear how you get the name of the document. You only get an identifier, so you need to dig into some global objects to find it. Global with respect to the class, of course. And then, of course, you need to define an ad hoc, a custom output type, which is a pair of types. So this is also, you need to declare a class for that. Okay, a class that contains two writable objects and that is itself writable, so it extends the writable interface of Hadoop and so on. Remember that you don't manage directly integers, you manage actually interwritable classes. You don't manage strings, you manage text classes that are writable raptors and so on. So there are a few problems to overcome. Okay, so for today I think that's all. If you have any more questions. Okay.